Hello students, welcome to Saraswati classes, and today we are going to discuss a very important topic in chemical bonding, which is Bend's rule. Okay, so over here, let me generalize first. Suppose you have been given a molecule which is AB5LN, okay, where A is your central atom, B are the substituents joined to A, and L is your lone pair, okay, of electrons. N would be indicating number of lone pairs. Okay. Now suppose we are saying in a particular case, the lone pairs it is 0. So in that case, we will say the molecule will be basically AB5. So basically your central atom is making 5 bonds with B. That means there are 5 electron pairs present in the molecule, and these are all your bond pairs, and your lone pairs, as I have stated, this is 0. So we know that steric number is nothing but the bond pair plus the lone pair. Okay, and if the steric number is equal to bond pair, then we say it is a regular structure. Okay, where I will say the shape of the molecule will be equal to the geometry of the hybridized orbitals. Okay, that is what I mean. Now we know from our previous lectures that steric number, if it is 2, we say the hybridization is sp. If it is 3, we say it is sp2. If it is 4, we say it is sp3. And if it is 5, we say it is sp3d. Okay, so this is what we know from our previous classes. Okay, now interestingly, whenever we combine one s orbital with 3 p orbitals and one d orbital, the hybridization of the molecule is sp3. Now sp3d. So sp3d can also be written as a combination of sp2 plus ped. Okay, and if you draw the hybridized orbitals, then it would be looking something like this. The sp2 orbitals will be disposed in space in this manner, where the lobes will be having a angle of 120 between them. Okay, something like that. So you can see this angle over here is 120, and the axial lobe will be placed along the z-axis, and this is basically your pd orbitals. Okay, and this one will be having an angle of 90 degree with the sp2 lobes. Okay, so these lobes which are having an angle of 120 among them, these are called your equatorial lobes, and These ones which are lying along the z-axis will be called your axial lobes. It is interesting to note that the S character of equatorial lobes is more than axial lobes. Okay, so this is something that we have to keep in mind. Now suppose we are considering a molecule something like, say, PF5, and let us calculate the total valence electron for this. So if we do that, we will say for phosphorus it will be 5, for fluorine it is 7 times 5, so the total count comes out to be 40. 40 is a number that is greater than 8, so we divide it by 8, and the quotient will be coming as to be 5, and it gets cancelled. So 5 is our number of bond pairs, okay, and so the hybridization we will say is going to be sp3d. So that is how one can calculate the hybridization of a molecule given to you such as PF5. So let us try this again for another molecule. Suppose we have been given over here SOF4. Okay, so for the total valence electron, we will say for sulfur it is 6, and for oxygen it is 6, 7 for the fluorine, and there are 4 of it, so times 7, and if we do the counting over here, this is going to be again giving you a total electron count of 40. So now over here, if it is 40, 40 is a number greater than 8, our electron pair, as we have shown previously, will be equal to 5, and that is going to be our steric number. And so again the hybridization will be sp3d. Okay, so if we have to draw the structure of PF5, so what we will do is we will place P like this, and we will draw 3 such bonds keeping an angle of 120 between them, just like that. So these angles are your 120, and you place the fluorine along the vertices of a triangle. That is what you have to keep in mind. And the other fluorine, okay, now you can see that the bonds that I'm drawing, these axial bonds, are a little bit longer, because, okay, so this is a little bit longer than the equatorial bonds. Okay, and this angle now from here to here, as I have said previously, it is going to be 90. Now, because there is all of these are fluorine atoms, so there is no problem. But if we have to draw the structure for SOF4, then we face some problem, which is, first of all, we know there are 5 bond pairs, so we draw such 5 bonds, and then these are the other 2 axial bonds. So here do we place the oxygen over here or do we place it here? That is one issue. Do we place it on the equatorial bond or do we place it on the axial bond? So let us draw the two structures and then we will discuss. So suppose one of the structure is something like this. Now remember, valency of oxygen is 2. So whenever you have oxygen in a molecule and there is no charge on the oxygen, so always try to make a double bond in between the central atom and the oxygen. So one is a sigma bond and one is a pi bond. Okay, so that is settled. That is how you have to overcome how to draw the bonds for oxygen with the central atom. All right. So this is one of the structure. What could be the other structure? You place all the fluorines in the equatorial bonds and then you have one axial bond making or attaching to the oxygen and the other fluorine is like this. Okay. Now here, how to decide which structure? Say this is called structure A and I'm calling this as structure B. Which structure will be the correct structure? So for that we will learn a new rule which is called Bend's rule. And what is that rule? It states that the less electronegative atom oblique lone pairs should occupy the equatorial bonds and more electronegative atoms should occupy axial bonds. Okay. Now keeping this particular rule in mind, you just need to find out what among fluorine and oxygen which is more electronegative, and your answer is what? You will say, sir, fluorine is more electronegative than oxygen. Okay, that is what you will say. En is indicating electronegativity. All right. So if fluorine is more electronegative, then it should be placed in the axial bonds. Okay, and oxygen should be placed in the equatorial bonds. Which are your equatorial bonds? These ones are your equatorial bonds. So oxygen can occupy either of these three bonds. Okay, there should be no confusion about that. And according to the rule, it should never occupy the axial bonds in this structure. Okay, so that being the case, we will say structure A will be our correct structure according to Bend's rule, and structure B will be the incorrect structure. Let's go for a few more examples. Okay, let's take PCl2F3. All right, or let's say let's take PCl3F2 initially, and then we will discuss PCl2F3. Now here also we can see if we do the total valence electron count, it is going to come out to be 40, and 40 is again greater than 8, so we will say steric number will be equal to sp3d. I mean, initially it will be 5, and so the hybridization will be sp3d. The question here is again, if you write the phosphorus atom and again you write the 5 bonds, so these are your equatorial bonds initially, and this is your axial bond. Okay. Now, according to Bend's rule, if we consider which one is more electronegative and which one is less electronegative. So here we will say obviously fluorine is more electronegative than chlorine. So according to Bend's rule, if we follow that, we will say the chlorine atoms will be placed on the equatorial bonds and the fluorine atom should be placed on the axial bonds. So this should be our correct structure, okay, and not this one. Suppose you have been given these two structures and then in examination they're asking you which one is correct. Okay, so they have given you these two options which I am drawing for you. Suppose you have been given this one, that one, and then you have a obviously a Cl over here, and the other Cls are like this. Okay, so if these two structures are given to you, just let me make the axial bonds a little longer. And if you have to judge whether, say, structure 1 is the correct structure or structure 2 is the correct structure, then following the Bend's rule again, what will you say? Fluorine is more electronegative than chlorine, so structure should involve the fluorine in the axial bonds, which are obviously these bonds over here, and the chlorine should be placed in the equatorial bonds, which is here. So this will be our correct structure, and obviously we will say our incorrect structure will be structure 2. Okay. Now let's check a few more examples also. So as I said, we will be discussing PCl2F3. So let's do that. So in PCl2F3, again using the Bend's rule, what we will say, draw the 3 equatorial bonds, axial bonds. Chlorine is less electronegative than fluorine, so obviously chlorine will be placed in the equatorial bonds and the other positions will be occupied by fluorine, and that should be our correct structure. Quickly, a few more examples again. Suppose you have been given a SF4, okay. Now let's do the total valence electron count of this. So we will say for sulfur we have 6 and fluorine 7 into 4, and that is going to give you 28 plus 6 is going to be 34. 34 is a number that is greater than 8, so we will divide it by 8, and out here it is going to be, so if we, this is going to be 20, it will be, the quotient will be 4, so obviously we have the number 32. If you subtract this one, then we have 2 electrons, and the remainder now that has to be divided by 2, that is the rule, and so we have another quotient which is 1. Now initially when you divide a number with 8, this thing we will say it will be our bond pair, and the remainder which we divided by 2 will be our lone pair. The total electron count, if you check, it is going to be 5 electron pairs, and so that means the hybridization again is sp3d. However, since we are having lone pairs over here, okay, so this is basically a B, all right, 4L1 type of molecule, okay, and this is not a regular structure, but this is an irregular structure. So whenever we say a regular structure, we mean all the electron pairs are your bond pairs, and whenever we say irregular structure, we mean some of the electron pairs are your lone pairs, and in those cases, we will say that the geometry, which is indication of the hybridization, all right, will not be equal to the shape. So out here, having seen sp3d, one would have thought that it would be having a TBP structure, which is trigonal bipyramidal. Let's draw. Now over here we have sulfur as the central atom, and remember it has one lone pair, so we will draw the bonds, all right. So now again the question is, do we place the lone pair on the equatorial plane, or do we place the lone pair in the axial plane like this? That is the question over here. So if you place the lone pair in the equatorial plane, this is the type of structure you will get, and if you place the lone pair in the axial plane, this is the type of structure you will get. Using VSEPR also we can solve this problem, that is valence-shell electron pair repulsion theory, as to predict which structure, say 1 or 2, is our stable structure, or we can use Bend's rule over here. According to Bend's rule, if we go back, what did I state? Less electronegative atom oblique lone pairs, okay. So this is what you have to use over here now. So the lone pairs also occupy equatorial bonds selectively, okay. That being the case, now if you look at the structure, we will say which is the structure which is having lone pair in the equatorial plane, obviously, or equatorial bond, obviously the structure 1. So this will be our correct structure, and this will be our incorrect structure, okay. So that is how we have to use Bend's rule to understand which structure is the correct one. Now this structure that you see, okay, remember, while predicting the shape of the molecule, we do not take the lone pairs into consideration. So this particular structure that you see is going to be looking something like this. We have to imagine it is something like this. That is going to look like that. So this particular shape, we call it as seesaw. However, if you compare this structure with a molecule such as SOF4, we will say this is trigonal bipyramidal. So the concept of Bend's rule is mostly applicable for predicting structures which have sp3 hybridization. Okay, so I will be ending my video over here, and thanks for listening and have a great day.